You're now experiencing data with Brian O'Neill. Experiencing Data explores how product managers, analytics leaders, data scientists, and executives are looking at design and user experience as a way to make their custom enterprise data products and analytics applications more useful, usable, and valuable. And now, here's your host, the founder and principal of Designing for Analytics, Brian O'Neill.
All right, welcome back to Experiencing Data. Today I've got Murray Cantor on the line, who is he has several different titles in your work, but you're currently the chief scientist at Aptage Consulting. But you have a significant background in engineering and data science. So can you tell our first of all, welcome to the show, but jump in and tell us a little bit about your background, Murray.
Thanks, Brian. I'm really glad to be here. I've been around a long time, so that I'll try to keep this reasonably brief. Back in the early 70s, I got a PhD in mathematics from Berkeley. And since then, I've been really interested in the dynamics of innovative products and the dynamics and economics of innovative products and systems. In the past, I was an industrial mathematician at Shell Research. I was a project and architect lead in IBM Workstation Division, putting out AIX 3.0. Former chief engineer of the service organization of Rational Software. Back in the day, Rational was a leader in software development tools and processes. Rational got bought by IBM, where I became a distinguished engineer focusing on development governance and analytics. Since leaving IBM, I founded Aptage, which isn't really a consulting company. It's a product company that delivers services for R&D project and portfolio management. I'm also the chief scientist at Hale.Sports, where we're looking at applying precision medicine techniques to sports performance. And I'm also a consulting mathematician to Pattern Computer, where we're doing state-of-the-art pattern recognition solutions for industrial customers.
You've covered a lot of different bases here, and I know you have some experience getting involved with user interfaces in addition to user experience. And in particular, when we had our pre-call, I know you had some strong feelings about explainability and AI models. So I wanted to talk about XAI a little bit today, as well as what are some of the concerns that you've seen coming up with AI-driven interfaces. We talked a little bit about you've done some work with airplanes, if I recall correctly, in airlines, and so you know something about that. Obviously, there's a heavy part of your work that's not necessarily interface driven or in front of the customer. You know, the deliverables are not necessarily interfaces, but you have those in mind when you're thinking about the outcomes that you want. There's a customer, a person involved, a human in the loop. So what is your process when you're working on these very complicated systems, leveraging AI? How are you approaching the user experience piece and delivering value and making sure, you know, the math and the science and the technology is actually delivering outcomes? Like, tell us about your process.
A lot of design principles are the same, whether or not you have AI. Mm-hmm. And AI just sort of raises the stakes. So there's a variety of outside-in design methodologies. I'm a fan of all of them, not particularly wedded to anyone in particular. But the real question that you have to often face in designing an AI system is the so what attitude. Mm-hmm. So I've discovered this pattern. That's interesting. Now what? I had an example of a company that could look at EKGs and predict whether or not you were likely to have a cardiac event in the next 6 months. And they couldn't monetize that. And the reason was, that's interesting, but so what? Yep. So this is part of the process question, which is people want to use artificial intelligence, machine learning, whatever, to do one of two things. They either want to make an intervention in the system, or they want to automate some process. that essentially things that people are doing that now they want machines to do. For example, reading x-rays would be an example of that. They just want to automate that process. So like any other good design thing, you say, why are we doing this? What is this for? And if it's to automate something, well, then you understand exactly the role. The person whose work you're trying to automate plays a role in a process. You just have to understand that role and what the performance parameters are for that role. And then how is the person who's being automated now interface with the system? And that's probably good guidance for how your AI should interface with other parts of the system. And how is that function getting measured? Well, that's how the AI should be measured. That you present that. If it's an intervention you're looking for, like what kind of treatment should I choose in this situation? This comes up in our sports example. What kind of training regimen, what kind of diet should people have? What you want to do is understand the decisions that are going to be made and report to the person who will make the decision what decisions are going to lead with what probability to what kind of outcome. And so you think a lot about designing for intervention.
This actually made me think of, I was at an event last night and you're talking about interventions with AI, and the speaker actually, he used like one of these scenarios, such as, let's say you have an AI that's doing image recognition and it's looking for cancer, at x-rays or some things, and it says, I think we've identified a cancerous growth here, and based on all the information, the recommended treatment is X, and the system is 75% sure that that's the right path. The doctor has 3 years of experience, maybe, let's say 3 or 5 years of experience, and maybe they've seen, 100 patients, and they feel like I actually think Y would be the better one, and they're relying on their gut and their experience, which is what we've traditionally used with medicine for a long time. And they took a survey of the room, a rough survey of the room, and the general feeling was like, if this was life or death, well, I'd still go with the doctor, even though the AI has looked at, maybe it's looked at 1 million scans and its success rate is quite high, versus someone that has less experience and maybe they've only seen 100 scenarios. Can you talk about like this friction in these kinds of recommender systems? Any way you might approach the design or the solution, or how do you talk to the customer when you're building that system about these scenarios? Does this ever come up in your work?
I think there's probably 4 questions in there, but let me tease them apart a bit.
Yeah.
Okay. So the first one is we're getting into how did the system make the decision, and understanding the causal model and the probability chain that led to the causal model is real important at this stage. So there's been a lot of really good work in the last couple of decades about causal modeling in general. There's the recent book by Judea Pearl, The Book of Why, which explains some of this history and some of this thinking. And so he actually recently had an article in Quantum Magazine for real AI, you've got to talk about cause and effect, as well as just matching parameters to training against parameter sets like image recognition. So what you're trying to do now is predict a future outcome, and you don't have the luxury of doing an experiment. So first, the doctors have not been well trained in this. And so most of the people I hang out with would actually trust the AI more than the doctors, believe it or not, because they understand these causal models. And part of the whole revolution of precision medicine is to get to a point that we have these predictive models based on individual parameters that are deeper than the kind of learning that patients have, that particularly young doctors have, which is they've seen a few hundred cases and they don't understand the confounding variables very well.
Mm-hmm.
So this is an education this is both research and education, and we're just at the beginning of these times. So I would like to believe that in 2 or 3 years, people would understand these things better, and the doctors would be more comfortable understanding the answer. Now, a better solution in both cases is if I'm given a 75% chance this treatment might work, and this treatment is very has risks on its own, and the treatment might kill me, what I would like is more evidence.
Mm-hmm.
And so a better solution in both cases is not to believe the doctor or the AI system, but to ask the question, what further evidence would I need to gather? What other additional tests should I take? What kind of biopsy should I have, or something that increases the probability of the prediction of the intervention being more favorable, of getting the favorable outcome, of choosing this. And so the goal at that point is both what the doctor should do is like in House on TV, the old series, he should order another, or she should order another test at this point, and if the test is expensive, so be it. Now we have enough probability of a problem that requires a treatment that the return on investment on a more expensive test really makes sense.
Mm-hmm. This actually dovetails into my next question. Let's talk about explainability for a second. So if the solution that the software that the doctor is, if it's doctor versus the software, even though it's not really what's happening here, we're both on the same side of the patient, hopefully. But
Yeah.
the software, if there was some explainability around the prediction in the model, and the doctor was able to help the customer work through that and understand why did the system come up with this, maybe to help the patient understand this prediction is based on a lot of parameters, that personal information about your particular health that factored into this, many more variables than maybe they've seen. I wonder if it's is that something that the doctor and patient work together through? And what is the role of explainability there? And I know you have some strong feelings about that. We don't really know exactly how explainability is working in these models. So can you talk a little take a tangent here about explainability and how that might fit into this situation?
Sure. So explainability clearly is really key, and we're in early days. So my strong opinions, which I shared with you earlier, is the companies out there, IBM, Google, Amazon, whatever. I'm not pointing fingers at anyone. The big companies right now are sort of jumping the guns and saying they have explainable AI when they don't. And it's going to take us a while to really get there. And if you think about it, if you ask a person how they made a decision, often they can't really even explain it themselves. They just say, well, I'm just going with my gut. What does that mean? Right? So explainability of anybody making decisions is actually hard right now. There are two issues here. One is that the early version of need for AI is just dealing with the problem that people have begun to notice, that AI classification algorithms of for things like hiring and giving loans or whatever that involve have biases in them. And what they realize pretty quickly is that the system today has a bias, and if you train an AI system to do what the system today does, it'll reflect the same bias.
Right.
And so you teach it, you give it a training set of how a bank already makes a decision. If the bank is biased, the AI system will become biased. Simple as that.
Mm-hmm.
Okay. And since we don't really know, a neural net, a deep learning neural net, literally is a black box. We don't really know what it's doing. What's happening is that it has literally maybe 1 million free degrees of freedom in the interfaces between the layers. And it has adapted those parameters, those interface layers, actuators, to match the results of the data using gradient descent algorithm of some sort, just standard, pattern matching. It's just like any other kind of regression thing. But it matched so many different parameters, and we don't know why, that we don't have. So looking at the neural net and understanding how decisions are really being made by that is still an open field. It's going to involve, in the end, two things. One is we're looking much more deeply at information geometry, information manifolds, and essentially the deeper mathematics of the structure of these neural nets. And that's being done. There's some really good work being done in the academic community right now, and that's really going to help. And we're looking at that in various other places as well. Small companies are looking at that, and presumably that's being looked at inside the big companies as well. So that's one thing. And the other is, and let me just make this other point, is that we're not going to have explainability until we also include the causal modeling stuff that Pearl and his colleagues are writing about. And it's the combination of information geometry and causality, which is going to lead to explainability. And we're just early days. I'm really looking forward to it. It's going to be great when we understand this more deeply.
I guess I would challenge one thing here. So I totally understand the issue with bias, right? If the training data was biased in some way, then explainability is only as good as what it learned from, right? It's the input, right? Garbage in, garbage out.
The explainability is really very simple. It matched the bias in your training set. There,
right.
I'm done. Now what?
Right. So are you saying that because of this, I would say understanding the risks of bias that may be in the system to begin with, removing explainability, if you have a model that can take advantage of having explainability as part of the experience and the display that happens there, I would posit that it's net better than the complete black box situation, because there's probably times when the explanation that is provided still requires human involvement, right? Like there might be that kind of level 2 analysis that the person does, especially if they get a recommendation or an explanation that they don't agree with, or they find is suspicious or whatever, possibly maybe to say, hey, this prediction feels weird. I want to feed that information back to the team that created the models, because maybe we're discovering where we have some bias. But I would net do you not feel that's net better than a complete black box situation?
Well, of course. And the point is, so we have to open up the black box, and there's some ways to do it.
Mm-hmm.
Okay. One is this, that was essentially my point.
Mm-hmm.
Yes, that explainable AI is very important, but it's not simple.
Mm-hmm.
And so the bias, a way to look at bias is to say there's some sort of latent variable in there that is resulting in lurking behind the decision process. Okay, and that's the language of causal models or whatever, where you're looking for the confounding variables. And if you suspect that race is an example, there are techniques for deconfounding the model for the bias, for those kinds of biases, if you can identify them. And again, that's more than just that, and you'll find that in the causality literature. Confounding and deconfounding of the data. And that's really cool stuff. And it's not being used enough yet, but it's on the rise. And we're going to see a lot more of that going forward, which is all great.
Mm-hmm.
The other thing is, though, that there is latent structure. If I try to if I look at the black box and try and open it up and try to understand the structures within that, in other words, is there a geometry to this model? And does that model, is that another way to explain how these confounding variables are coming into the picture? And there's research going on in that too. And that's what I was mentioning about the information geometry. Right now, the neural nets are complete black boxes. We don't want them to be. We want to understand what the deeper structure is of those, and that involves information theory and some modern ways of looking at the geometry of the parameter spaces, which there's something called topological data analysis. There's information manifolds, stuff like that, that is going to give us some deeper insights into into the effect of those confounding variables. So all I'm saying is, yes, let's not jump the gun. Let's not pretend we have it yet. Let's work on it. And in the meantime, having a person in the loop is always a good thing.
We had talked a little bit about the I forget how I came up, but the 737 MAX situation. I had read an article at the time, and I don't know, somehow that came up when we were first talking, and you had some opinions about designing the system, especially a system in this case which was opaque to the customers, and it caused death. Unfortunately, it was a poor choice. You have some strong feeling. There was a New York Times article that just came out that really unpacked, at least from the writer's perspective, about what happened in that scenario. And my general takeaway was that there was fault. He felt there was strong fault on the training side of the airlines in terms of who they're putting in the cockpits to run these systems. And there was also software, there was an interface problem with how this system was opaque to the operators. So can you talk a little bit about this and some of your opinions about designing the system and an quote intelligent system that's supposed to be helping the human operator?
There's no single fault. There's lots of faults that went into the 737, in my view, fiasco. It's still playing out. So here's the situation. Boeing needed to put a new kind of engine on a fuselage for which it wasn't designed. They essentially jury-rigged that by saying, okay, we've now taken a stable aerodynamic system and made it less stable by putting on these engines for which it wasn't originally designed. And we're going to treat this as an upgrade, not as a whole new system. And we're going to fix the instability with one sensor and some software. And we're going to put this out to the whole world, and and we know that out there are going to be pilots of a whole range of capability. But we're not going to tell them, by the way, we're going to do this. Okay, so this opens up all kinds of issues about failure of process and whatever. And now they're opening up a safety board and whatever. Blaming the small airlines for not having enough training is really missing the big point in this. So I was not impressed with the New York Times articles. I think they really missed the whole main point. So what happens when you're designing an airplane?
Actually, let me stop you real quick, just in case listeners haven't read up on this. I'm going to summarize it real quickly. Feel free to correct me, but the long and short of this, as I understand it, the 737 has been around for a long time. They wanted to create a quote better version of it. And if you're an airline, you don't want to create quote a new airplane, because as soon as it's a new airplane, it has to go through way more a long checklist of approval before it can be flight ready. And so instead, you call it a 737 Neo, a Max. You make your adjustments to a current plane, so it's more like an adjustment, and you don't have to go through the same hoops. So in this case, it was more fuel efficient, better engines, but because of the new hardware they wanted to put on the plane, this better engine system, and to get those efficiencies, they needed to counter some of the effects that were the aerodynamic effects by putting in a software, what turned out to be an automated software system that would control for some of the new variables that the engines introduced. Am I correct? And that's kind of like our starting point for this?
Well, close enough. What they did, the new engines introduced instability in, I think it was the yaw, or one of the three dimensions of how airplanes transform. I mean, it was not the yaw, the attitude. And so what you want is that a airliner essentially will glide, even if an engine fails and whatever. It has to be real robust. What you don't want is an airline that, a jet fighter is a whole different thing. You don't want those to be able to turn on a dime and win in a dogfight. For an airliner, you want it to be very stable, not very agile, but safe. Probably would do real badly in a dogfight. So what happened is they broke their standards of stability, essentially. And they knew that, and that's why they put in this automated system, which was going to account for that by adjusting the flight services. The problem. So now what we have is something a pilot would normally, if the plane is at the wrong altitude, that is, it's heading up or down incorrectly, you allow the pilot is supposed to detect that and make the correction and manually override it. And so what you have, the total system is a combination of the plane, its sensors, its software, and the pilot who's supposed to do the right thing under the right circumstances. The problem is, even what we can seem to have detected, even if these were, by the way, some of the pilots are pretty well trained who had these problems, is that they would do what they were trained, what they should have done, and the plane, they didn't know how the plane was going to react to those actions. And so the interface between the plane and the pilot was broken. A predictable action of a pilot led to a worse problem for the plane.
Right.
And the designers of the interface should have seen this coming, and they should have either put in very severe training things, which they didn't, or they should design a system for which, when it gets into instability, it essentially leads the pilots doing the right thing if it can. It turned out this thing, there was probably nothing the pilots could have done. In terms of interface for systems design, what you want is you imagine that the operator and the vehicle design are really together a total system which is supposed to be able to behave in some sort of effective, safe manner. And you design the interface to the operator in such a way that reinforces that. And you see that in like the modern cars with the lane keeping and the automatic speed controls on the highway and a whole bunch of other things that reinforce the right behavior of the driver. And eventually we're going to get to, even more and more autonomous driving, particularly on long haul trucking or something, where in fact the interface to the driver, there may not be any driver at all. But in the meantime, what you want is that the feedback loop between the driver and the vehicle is such that they both can play their role in such a way. So here's another example. Suppose you're in the air and you're about to have a collision, and the radar detects that a collision is imminent, and the right thing for the plane to do in this case is to veer upwards and to the left, because that's the convention. If two planes are about to hit each other, there's some convention about how they're supposed to change course to avoid hitting each other. You want the plane to do that automatically, and you probably don't want that overridable by the pilot. And designing that level of experience and interface, and you want the pilot to understand what the plane is doing and be comfortable with the fact that that's what's happening and be glad for it. Right? So you design a system like that.
You're listening to Experiencing Data, the podcast that explores how design and user experience make enterprise data products and analytics applications more useful, usable, and valuable. Your host is Brian O'Neill of Designing for Analytics, designer, UX consultant, and advisor to the business leaders behind custom enterprise data products and analytics applications. For more information, visit designingforanalytics.com. If you're enjoying the show, help Brian out by rating it on iTunes. And now, back to Brian.
Does that make sense?
Yeah. No, I understand what you're saying.
And they didn't do that for the 737 Max.
Yeah, I mean, it was unfortunate. I think the article is worth a read, whether you see it as a human, if you see it as a training issue, putting pilots in the air with not enough experience, or mostly software, or a combination of the two. It definitely.
Well,
go ahead.
Yeah, I think blaming the pilots is just the wrong thing. The aircraft manufacturer knew the population of pilots they were selling this plane into, and they should have accounted for that.
how do you in that situation then, like, I mean, I don't want to speak on behalf of Boeing. Obviously, I can't in that case, but there's always this balance between a prescriptive situation, like an automatic system that's going to predict and potentially actually enact some kind of action versus that, human intervention thing. So is there a process that you think about when you approach this with a client, for example, about when and how much human intervention are we going to allow in the system, especially if it's like, do we want to expose that knob and let them dial it in however they want, the end user, or is it really a knob that we shouldn't let them, but we'll give them a different knob that they can, work with? I'm trying to simplify this down a bit, but there are times when you probably do want that human to be able to take override and not. Is there a general way you go about doing that in your work to kind of work with a client, maybe a customer who's asking for a system that's does some automation? How do you approach that?
Yeah. So first of all, you explicitly design these scenarios as part of the specification of the system. And this is what UX people do and whatever. So when you're looking at systems decomposition, you look at the total system and then you decompose it into the vehicle and the operator, for example. And you do the discipline of systems engineering with that kind of decomposition. But to answer your question more fully, is that's why there are simulations. And so what you do is you build a faithful simulator and you run a bunch of you do system tests with simulations. And you have pilots flying the simulated airplane under enough of these different scenarios to validate that the system is airworthy in a way that pilots will react appropriately. So you test it just like anything else. And the answer is, here's the spec. You run system tests with simulations. And if people are crashing the airplane in the simulations, you update the design and do something.
Sure.
Really. And this is a standard kind of thing. It's a discipline that somehow got lost somewhere in the process. I don't know exactly what happened inside Boeing, and I'm not an expert who studied all the evidence and everything. I'm drawing some conclusions from the outside looking in. But this is the reason you have those kind of systems is to avoid exactly these scenarios that happened to the 737 MAX.
Yeah, you basically summarize the same thing that designers, most software designers are, good ones, at least the ones that are doing what we should be doing is validating the system that you're designing as you go. And
That's
so
right.
You're running, we usually call it a usability study, and sometimes it's not always understood by non-designers, but you're not testing the people, you're actually testing the system. You're testing often the interface.
Exactly.
It's not a test. In fact, sometimes they tell you to avoid using the word test when you're talking to a participant and you tell them it's a study and we're here to evaluate a piece of software or, in this case, a cockpit to figure out if it's the right design or not, so that they don't feel like they're a rat in the maze kind of thing. It's really studying the maze.
Yes.
So
that's perfect. So think of it like this. That's exactly right. And that's really, it's so important that this idea keeps getting out. See, when you're putting out a system like the aircraft, you have control over how the aircraft works. You don't have control over who's going to fly.
Hopefully there's some control, right? I know what you mean, but that's why we...
No, but you don't. I mean, there's regulations and whatever, but you can't stop. So the thing is that what you do have is you know something about the pilots, but they will have a range of experience, a range of capability, and there's some likelihood, small, that you're going to put a pilot in there who's barely capable of flying this kind of plane. The odds of that eventually happening are very high. And the plane should be robust enough to deal with that. So what you do is you plan for the range of capabilities. And it gets into the problem. And the more airplanes you sell, the higher the probability is that one of these poor pilots is going to end up flying it. You see, and this happens, by the way. What's interesting is like there was a whole business with Toyota and their quality control, but actually their quality control was probably about power for the industry, but they sold more cars than anybody else, so more problems were beginning to show up. because they had more cars in the field. And so so what they realized was they had a higher responsibility than the average car maker to make their cars safer because they were selling them to a bigger population. This is really fundamental to understanding user experience and design. Is you ask the question, what is the population of people who are going to use this, and what is their range of capability?
Yeah, and you're not always going to, testing one person, or testing the system with one person is not usually enough. And there's a lot of times people ask, well, how many people do you need to study? My favorite answer to that is like, how many will it take for you to believe that the system needs changing, or is it wrong? There's some math there,
Right.
but typically you can test usually, 5 to 20 people, somewhere in that range. You're going to start seeing patterns typically emerge pretty early. And if you keep seeing the same thing over and over, an issue, then you probably know it's time to make an adjustment there. But I don't know that that the people working on all these systems are always thinking about this kind of validation. I don't hear it. I mean, this is normal for the design world. This is like kind of normal at this point for most software design, that you're doing some type of validation work. It's not so much in the data science people that are working on some of these kinds of systems, especially if there's not a large user interface component. So I know part of your work, you help clients develop data science teams. And so talk to me a little bit about some of the non-technical skill gaps that you're seeing with people in the data science and analytics field. Is this one of them? And what are some of the other ones that you see?
Well, what's really interesting about this is that, like in the simulation tests, you're not going to test 100,000 pilots, right? And so what you have is a problem with which you brought up, which is really a small data problem. How do you draw the right conclusions from smaller data sets? And this is one of the advantages of these. This is where Bayesian techniques are really important, which is and these causal models, which are based on Bayesian techniques, which is what you don't get is, the way I like to put it is, it's not garbage in, garbage out. It's uncertainty in, uncertainty out. Right. And the question is, the question is, how many people do you have to test? And if you're smart, are you testing an inhomogeneous population, so that if you're only testing expert pilots, that's not going to teach you very much. And so putting attention to stratified methods of dealing with more carefully selected populations and things. Right now, people are trained to work primarily with big data sets and we run them through these deep learning algorithms and stuff. The skills you need for this, dealing with these smaller data sets where you can't run big blind experiments and stuff. The other thing you can't do is put 100 good pilots and 100 bad pilots on two different planes and see how many of them crash.
Right.
Right. Maybe you can in the simulator, right? But a lot of experiments you can't do. So training. So one of the things which we're seeing not a lot of yet, but there should be introducing causal models into these organizations where people have been trained in big data techniques is one of the things I find myself doing a lot. Is saying, okay, we don't have the data for that. So now what can we do with the data we have, or data we can afford to get, using more sophisticated probability theory? That's the first thing. So I end up doing a lot of that, because that's really all over. That's really all over the place. The second is what I just generally find is that there's a lot of, and I think this is just again sort of the maturity of the field. Neural nets and the like work better than we understand. We don't understand why they work as well as they do. But what happened is we just sort of got across some sort of computational barrier, and suddenly they started working because we made them big enough. Okay. And then we started training a bunch of people on how to build big neural nets with all the ad hoc techniques that are out there. And there's a bunch of ad hoc techniques out there. And people understand that right now, working in these in these various neural net environments like TensorFlow, whatever, is really just mostly a matter of trial and error for building and applying. Eventually, it's as much. I wouldn't call it an art, but a craft. It's not yet a science. It's like the early days when they were building engines before they understood what thermodynamics was. We're in that stage of this industrial revolution we're going through with augmenting people's ability with machine learning. But right now it's more of a craft than a science. And so we have people out there who are really good at working with these techniques and algorithms, but they don't necessarily understand. They're essentially a solution looking for a problem. The people with the problem start asking people, they'll just start saying, well, let's throw AI at it. And a lot of what will happen, we've seen this over and over again, is that people will throw the algorithms types that they know. It's the hammer's looking for a nail. When they don't have the depth to understand that particular technique isn't likely to work with this kind of problem. And meanwhile, the executives don't know anything, don't know any better. And so getting to a point where we have senior data scientists who have the experience to know which of these various techniques and which of these variants of these techniques and how to pose the problem with the executives in a way that it can be answered. That right now is still an evolving capability in the field. And so I find that building, I think you do this in your own practice, is that having webinars where you sort of inform each other with the various stovepipe functions, learn how to collaborate and develop an answer that meets the business need and is still feasible with the kind of data they have. And the other thing that you often see is, I have this kind of data, it must be useful for something.
Right.
And I much prefer the other question is, I have this question, what kind of data do I need to resolve it? And what kind of techniques? And how is that done? And maybe I need to be collecting different data than the data I have. So working, again, outside in is a technique that a lot of these people aren't taught. They're taught, here's your data set, do something with it. Not, here's my problem, what data do I need in order to do something, to get what I want?
Yeah, this problem, I hear this a lot. My perception is that I feel like business stakeholders sometimes think like, if I hand the data warehouse to a data scientist, they will go look at all the stuff that we have in there, and then they will tell us what kind of magic we can create from it. And their perception on the other end is like, I'm waiting for you to give me a great problem, and I'll let you know what data we need to solve it when you hand it to me. And so everyone's scratching their head, and we get these, 85% failure rates on, AI and big data projects. And because there's something missing here, which is understanding what problems could we potentially solve, what needs are there, what are the business objectives, what do people need or want to do, with these systems or products. And that's a space where I think designers can help out. We provide that. The deep empathy part of it really helps you ground some of this work, and so that is partly what I try to work on with, at least with the seminar, is how do you learn how to ask the right questions to a business, back to a business person if they are giving you a vague question like, can we have some machine learning? Does our product have ML in it? We want to be able to say it has ML in it, which is not the right. But how do you unpack that and get to something where maybe there is a viable way to use ML to create a better experience or some business value, but they don't know how to ask the question yet. So back to what you were talking about with like the skill gap here, is it the situation where the young data science talent only knows how to use I'm looking for places to use a random forest classifier because that's what I learned, or it's they do have a wide enough technical knowledge about the different types of algorithms to use, but they're not asking the question, like they're going in with their favorite one to use or the one they know the best about because they're not really sure how to use the other ones, so they try to shoehorn it in to every problem they see. Is it a lack of technical and the soft skill piece to figure out the problem space, or can you unpack that a little bit?
Well, first of all, of course it varies. right? But I've seen people, you look at these books that say learn TensorFlow in a day. Yeah, right. I mean, you see these things out there. And, so that's the one end. The other end are PhD students who understand these things very deeply, right? And they're right now being swept up by the big companies, and which is a good thing in a way, right? So that ranges. What I find is that even with solid people, there's so many issues about vocabulary and overloaded terms and whatever, is that neither side has actually been trained to talk to the other.
Right.
And it's more like that. And this is what you do, I think. One of the techniques I use in bringing machine learning into an organization is I have the team, right? The members of the team write a science fiction story. And this is like, the whole point is you're trying to create a vision of what the enterprise would look like in 5 to 10 years because they have machine learning. What is it that the enterprise can do that they can't do now? What is it they need to have done that they can't do now? And you may discover that it's just achieving better performance. It's an idea of we're going to minimize the amount of time someone waits for a train all times a day. And so we're going to have a much more sophisticated allocation of resources than we have now, where it's always on the same fixed schedule or something. And then we start going from, okay, what would a system look like that fulfills this vision? And we work our way down to various AI approaches to try. But again, it starts at the usual place, which is everyone should have the same vision of where they're headed to. And I find the story technique is a way to do that.
I think that's super awesome. I love that. I sometimes in my own practice call them North Star designs. And part of it is like, especially when you have technical people in the room at the early stages, when we're doing a discovery and even starting to sketch solutions out, is to take implementation hats off and just put it aside, because you don't know, you may come up with shoot a moonshot, but from the moonshot, you might find out there's these little tangents that are actually feasible things. But if you never let yourself dream that big, you'll never hit those the small incremental steps that you may be able to take. So that I love the idea of thinking big, and then reality will always kick in. The feasibility will kick in very soon, but there should be some time to let our minds go big.
Yeah, and then you drill them back down to reality. Right. But until you know what that is, you really can't ever get to a big picture plan. So what kind of organization would I need now to implement this vision? And then you get into those kind of issues as well. But the vision is where you start.
Yep. Murray, this has been a really fun conversation. I wish we could keep going more on this. We've covered a lot of great topics here. So is there if someone wanted to follow your work, or do you write much, or LinkedIn, any social media, how could people stay in touch with you?
I do write. I have PCI is about to publish one of my white papers, Pattern Computer. The best way to get me is just on LinkedIn. I have an admirable enough number of followers. Anyone who wants to connect with me, I'm happy to have them do that. I don't update my profile all that often, but I do put out papers, and I do post them when I do on LinkedIn.
Awesome. Great.
So that's probably the best way to find me, Murray Cantor, C-A-N-T-R.
Great. Well, I will put your link in the show notes, and thank you so much for coming on Experiencing Data and sharing your background. It's been really fun to talk to you.
Oh, Brian, it's been a real pleasure. Thank you for having me.
Take care.
We hope you enjoyed this episode of Experiencing Data with Brian O'Neill. If you did enjoy it, please consider sharing it with the hashtag #ExperiencingData. To get future podcast updates, or to subscribe to Brian's mailing list, where he shares his insights on designing valuable enterprise data products and applications, visit designingforanalytics.com/podcast.